All right, here we go. Okay, so this is out of a Go view. So it's under tests and exams and it's kind of overview of what's going to be. So it's going to basically covers modules 1, 2, 3. And I assume there'll be more questions from 2 and 3, chapters 2 and 3, which is productivity and forecasting. Because chapter 1 is more of introduction. Okay, so you pay attention to those two chapters more. And some multiple choices, probably, I don't know how many short answers. Could be very few short answers if there's, and problem solving, like 2, 3 questions combining different multiple options that you need to answer, like a forecasting. Okay, forecasting question, you have a problem, then you need to solve based on whatever technique, one of those, one or more, of course, techniques that you need to use. And productivity, same thing. In terms of finding productivity, you can use different, depending on the situation, you're going to find the productivity, either single or multiple factor for the problem. And forecasting accuracy measure is not that, I think this is more of statistics, but I think it's pretty useful for us because so that we can measure difference between actual and forecast, right? So in terms of measure how accurate your forecast is, that's from the statistics. Either you're going to use the average or mean square, or you're going to use a percentage. So that's the difference. Average, mean square, and percentage. Okay, so very simple. So I don't think I covered from this session. So let me show you what I mean here. Okay, so this is the first one, mean absolute deviation. Again, we try to find the difference between actual and forecast, right? So you have so much of actual, but you forecasted whatever different number. So we try to find the error between those. So to use it, first one is mean absolute deviation. Pretty simple. You take the actual minus forecast, then divide by, number of items. So it's the simple example. You have 3 actuals, 3 forecasts, right? So you just find the error between those two differences, matching sales and forecast, then divide by n, which is 3, then you get the average, right? So we have like 6.67. That's the answer. But how are we going to interpret? So we can interpret like on average, we are off about 6.67, which is approximately 7 units. Okay, assuming we are dealing with the units. So it's pretty straightforward. And the second method for measure the error is mean square. So just like a forecasting, we can increase the errors, increase the mistake, increase the differences, so that we can kind of magnify, for the problem or for the case that you're working on. So you just square whatever the error. So that's what we're trying to do. But I think in the book, textbook use the n-1 in terms of denominator, but it can be just n. Okay, so depending on the situation, I think statistics, they prefer n versus n-1, but as long as you use this consistently, that's fine. Okay, you cannot use n-1 and for the same problem. You have to use consistently, either using n-1 or n for the denominator. So again, same example, you'll find squared of the error, then you multiply by n-1 in this example, then you're going to get 75. Okay. So how are we going to interpret Actually, this is 75, right? 75. So on average, the forecast has a squared error of 75 because the unit we're dealing with the average was different because we squared, the error. So that's how you're gonna interpret so that you can compare with other, mean square error if you have it. So that's the mean square. So as long as you square the error. The third one is mean absolute percentage errors, meaning that we're trying to find the percentage out of this error term. Okay, so basically this over here, what we're trying to find is a percentage. Then you divide by number of items. Okay, n. So again, using the same data set, you find percentage of error, which is difference between actual and forecast, which is 5. Then you divide by 100. The same thing, then you find percentage errors for each item, then you divide by n, and you get the average percentage, which is 6.6. So we can kind of interpret our forecast was about off 7% on the average, okay, because this is average of those error terms. All right. So that's the 3 different techniques that we can use to measure the difference between actual and forecast. Any questions? So if you, for the actual tests, I think pretty straightforward. I may give you some examples like this. Of course, it can be a little bit more advanced because this is way too simple. Then you're going to find the error accuracy in terms of using MAD, MSE, or MAPE. Then again, I think I need to tell you, I'm going to give you all those relevant formulas so that you don't have to memorize. Okay, so. All right, so that's about Proctor tests. Any question about the tests? We good?
Hi, it's Axel. You said there was gonna be some short answer questions. Can you
Could it be?
explain like
I
what
haven't
you?
decided yet
Okay.
for that one, but I have other questions, but that one, but if there is one, maybe just, just a couple of questions out of productivity or forecasting.
Okay, thank you.
Yeah, but I kind of doubt. So. All right, any other questions? All right, what about assignment 4, by the way? Assignment 4 due this week. I think this is the one. No, this is assignment 3. This is assignment 4. There you go. Yeah, there you go. Yeah, I think this is the one. Yep, reliability. Have you started yet? Or any questions? Okay, so let me just give you some overview. I believe these questions, the homework questions, are the chapter 4S, which is more reliability. And the other chapter is actually chapter 4. This is S, right? It is S, yeah, reliability. They call it supplemental to chapter 4. I think I pretty much focus on reliability, which is supplemental to chapter 4, rather than the main chapter 4. So all questions are from 4S, reliability. So if I can go over some of those questions quickly. So we're trying to find out the probability, reliability of this system will work. Okay, so we have two different components, okay, kind of connected. Sometimes we have backup if this component does not work, and then we try to find the reliability of those situations as well, okay? So we have two rules, if you read that chapter, hopefully. And rule 1 is two or more events are independent and success is defined as a probability of all events occur, meaning that both of them work fine. Okay, then all you do is just multiply those reliability, okay, which is simple. Just multiply, okay? But the second situation is more of questions. Only one works out of those two components, then what are we going to do? So that's the problem, okay? And basically, in that case, if only one works, and we're going to add the probability, then subtract the overlap, okay? And this is the formula. So you have a probability of A, okay, plus 1 minus probability of A itself, okay, so that it will kind of eliminate duplicates. Then you multiply by reliability of B, okay. So that's kind of give you reliability, probability of only, right? There you go, okay. A little bit too small. There you go. All right, so that's what happens. So question number 1, under A, we're going to find the probability this system will work under this circumstances, which is 0.9%, 0.9% of time it works. Then all you do is just multiply by 2. Then 81%, and both of them will work. Okay. Then B is the question actually that we need to answer more carefully, B and C. Okay. So each system component has a backup, okay, just in case, right? And backup has 0.9 probability of reliability. Then a switch that is 100% reliable, okay? So if you need backup, then the switch will work 100%, okay? But backup itself has a 0.9%, okay? So here's what we're gonna do. And we need to find two circumstances for each component 1 and 2. So first one is component 1, second one is component 2. Actually, it doesn't matter in this case, right? Because both of them has 0.9, probability, which is fine. So all you do is just find if both of them works for work component 1, then just multiply by each, because you have switch of reliability 100%, so you multiply by 2, same thing. Component 2 has backup, so itself multiply by 100%, then you got 0.9. This is the case that both of them work, right? Both component and switch works. Okay. By the way, switch is a mechanism that the backup will kicks in. So that's how you're going to set the percentage here. Okay. Okay, so second probability we need to find for component 1 itself, it work, or if it's failed, then backup must work. So one or the other works. So that's why we're going to find probability for. Okay. First case was just both of them work. Second case is just one of them work. So how are you going to find it? Oops, there's a typo. That's 0.9. There you go again. 0. Okay, 0.9 plus, I think this is a good example. So this is the success, probability of success is probability of main works. Okay, there you go, 0.9. Then plus main, this is the case of main fails, right? Because 1 minus 0.9. So this 0.10, that's the failure probability, right? Then you multiply by backup probability, which is 0.9. Okay, that's how you're going to find the probability of component or backup works. Then you just add them up, then you find 0.99 for component 1. Same thing for component 2, either itself or backup works. This is how you're going to calculate, because this is a main, when main works, and this is a main fails, right? 1 minus 0.9. Then this is probability of main and backup works. So that's why you multiply by. Then you find the same thing, because it's basically we're using same number, which is 0.9 and 1.0 for the switch. So we found both components will work, will be 0.99, right? Both, here you go, 0.99, 0.99. So probability of both components will work is just multiplied by 2 of them, which is, what is it, like a 0.9998. I didn't go that far, I guess. Okay. So that's how it works. So it's for reliability, that's the thing. Either you're gonna just multiply by both of them for, in the case of, all event works, or only one works, then you do this series of check, which is the main, when the main works, and main fail, and multiply by backup. So I think that's essential for reliability check. Okay. And many of these questions here are just applying the same formula. Okay. Same thing for C, but this time 0.9 probability for the backup and 99% of reliability for the switch. Okay, so so we're going to find the probability of component 1 and switch. 0.9 times 0.99. So give you that. So component 2 is exactly the same, because we are using the same probability for backup and switch. Then we do the same thing here. This is the main probability. Then this is the case of when main fails, and this is the probability of backup when backup works. Then you're going to find this probability, one or the other works. Okay. Then at the end, you're going to multiply by both of them that you got from each component. Right, then you'll find the probability of, in this case, which is 90% probability for the backup, and switch will work only 99%, not 100% this time. So the number will be smaller. Question 2 is pretty much straightforward. We have 4 components for this product. And I don't know why I choose this one, because it's very simple. Well, I guess it's okay. So you don't have to think too deep, because it's just pretty much straightforward for finding probability of all connected parts. There's no backup, no switch, anything like that. Okay, because all parts will work simultaneously. Third one. Okay, so this product is robots this time. This robot has 4 components, and each component has reliability of those 0.98, 0.95, 94, 90. So that's what we're trying to calculate, okay? So all of the components must function for robot operate effectively. So our first one is compute the reliability of the robot. When all components work, right? Then you just multiply all your reliability at the same time. Pretty straightforward, because there's no other options attached, like a backup or failure. Okay. But question B and C has some options. Okay, you need to pay attention to. So they want to add a backup just in case. So the question is, to achieve the highest reliability, which components should get the backup? All right. So first thing you need to do is you need to find each component's reliability. Okay. .98, 0.5, 0.94, 0.90. So here we go. So first one, component 1 is 0.98% of reliability. So we're going to apply rule 2, because this is the case of backup, right? So we need to, again, this is the probability of main, then there's the failure, the main fails, but the backup success, right? So you multiply those 2, then you'll find the mains, and just one of them works. So you find 99%, 99.6. Okay, so what we have is the main fail with 0.02, but backup is working with 0.9, 0.98. Right? That's what we found here, right? Okay. So reliability of robot based on the rule number 1, because this is assuming all components works, because we are looking at this calculation for component 1, right? Component 1. So we take that, the calculation we got, then multiply by other components, which has no backup, and see how much you get. So you compare this amount, then you go for the highest reliability. Any question about that one? Question number 3. This is the same as previous one in terms of calculating, backup and main using this formula. All right, that's C, question number 3C. For one backup with reliability of 0.9 can be added. So we want to add a backup, but the reliability has 0.92. So which component we have to use this so that we can get highest overall reliability? Because if you look at that, we have 4 different cases, right? 4 different components. And by adding this backup, which component can take advantage of most? I think that's the question. Whether it's 0.8 or 0.0. I think without calculation, the instinct is just go for lowest, right? Because the lowest, by having the lowest, then you're giving backup, then you can increase the reliability, I assume, So that was my kind of intuition, but that all depending on how calculation comes out. So you calculate same thing like we did it previous step. The calculation goes for using rule number 2, which is just either main component or backup will work. So okay, main plus this is main failure and backup works, then you get again the probability for one or the other works. Then to find the reliability of robot itself with component 1, multiply all those 4 components, then you'll get the answer for component 1. You do the same thing for component 2, then you'll get reliability, compare all those 4, then you'll find the highest reliability that you get. So you can answer the question for you want to add a backup with a reliability 0.29, and which component will get the most out of it. Okay. So that was question 3. Question 4. Question 4 is more of normal distribution question. Okay. So office manager received a report from consultant includes sections on equipment replacement. Okay, so this matter of scanners, right? So scanner has a lifetime. So this particular service trying to help the customers before the scanner reach lifetime. So they try to measure, what's the kind of average working time of the scanner in terms of number of months of service. Okay, this is before 30 months of service. There's the between 40 and 45 months, and also mean life plus or minus 2 months of mean life. So there's a mean number. I think a mean is like 41. Okay, the 41 is given. So basically what it's saying is the scanner lasts about 41 months. So at 41 months, it probably going out, meaning that it could break down or it just stop working. It doesn't necessarily mean will fail, but will stop working. It's really hard to put it that way. I don't think it's really failure, but it's more like a stop working or it will last until 41 months. So, and also standard deviation is 4 months. So on average, they are spread out about 4 months, from the mean. So it could be 37 or 45, okay, in terms of the how much, spreading out from the mean. So this important data is already there. Mean is 41, standard deviation is 4. So you're going to use the normal distribution calculation, which comes from I think I have it. Oops. There you go. All right, so this is normal distribution formula. Okay, so T minus mean over standard deviation. Okay, the T is the number you are putting in. Okay, the Z is the score that you're trying to find. So with the Z score you find, you're going to find probability from the table. If you recall statistics course, you play with those, Z score, T score, then you go back to, at the end of the textbook, you find the table, Z table, T table, then you find the spot that crossing, the Z score. That's what it is. So this is exactly the same thing, okay? So we are plugging into this formula, which is 38 minus 41. 41 is again the mean score, and 4 is the standard deviation, which is given. So mean and standard deviation is given. So all you do is just plug in 38, which is the number that we are trying to look at, 38 months. Then Z score comes out as a 0.75, which is 3/4, right? Which is negative actually. So it comes up negative 0.75. So we need to find the probability of this Z score from the table. Okay. And which one we can use it? I think we can use it out of any textbook that has a Z table or T table. This is our textbook. That's Appendix B. Appendix B. So if you go to Appendix B, you have a table A, table B, B1 actually, because that include negative. So you go Z score, the negative 0.7 is there, then across here 0.5, which is 0.2266, right? So 22%, 23% almost, right? So that's what we found. Okay, so what does it mean? It means that 23 out of every 100 scanner will stop working before it reaching 38 months. Why? Because we are using 38 months as our T score. Okay. So that's how we're going to interpret. Even though the mean is 41, because this is only it doesn't reach 41 yet, the 38 month, right? So B is between 40 and 45. So all you do is find a Z score for 40 using a Z formula, find the probability, which is in this case 40%, and find again Z score for 45, which comes out as 84%. Then you subtract it. Subtract from 40 to 45, the case of 40 to 45. So that would be 84% minus 40%, approximately 44%, right? that will be 44 out of every 100 scanner will kind of stop working between 40 and 45 months. And this is case of plus or minus 2 months of mean life, which is 30, meaning that 39 to 43 months. So you find again probability for 39 months from the table. Same thing, probability of 43 months. So then subtract it, right? Subtract 39 from 43. So whatever you get, the difference between those two, meaning that the percent of those scanners will last within 2 months of the mean. So between these two numbers, I need to last, what is it, like 30, 39%, 39 scanners, right, will last. The last one is just what they call MTBF, mean time before failure. Okay, this one is pretty straightforward. Okay, we try to find out availability of machine or device or process. Okay, mostly machine. Okay, so we're trying to find how long machine will runs before break it down. So the first case is 40 days, but average repair time is 3 days. So we plug into availability formula. Okay, so you take that MTBF value, then you divide by MTBF plus MTR, which is 3. Okay, so 43, that's the denominator. Okay, so 40 divided by 43, then you get the percent. Same thing for the second one, and you get 300 over 306, then you get the whatever percent, and that's the percentage of machine will run without any problems. So number 5 is, I think, is pretty straightforward. Okay, any question? Hopefully, those make sense. Any question and comments?
I'm good, Professor. Thank you.
All righty.
Same, I'm good. Thank you very much.
All right. So any questions at all? Number 5 was your favorite? Okay, straightforward. Well, hopefully, in the actual life or at the workplaces, you get those kind of problems, then life is easier, right? But things are not easier these days. All right, so if you don't have any questions, and good luck tomorrow. And just in case you have problems or issues arise during the tests, don't panic and just talk to your proctor and trying to solve the problem. And if you can, some reason, if the problem persists and you couldn't finish and you need to talk to proctor, so proctor can record whatever happens so that we can do something about it. All right?
Thank you.
Okay. See you next time.
Thank you.
Bye-bye.